Hello people, welcome to the second tutorial for solar envelope tools. These tools were created to help architects and designers to take in consideration different solar access regulations during early stages of the design process. In this tutorial, we are going to create solar envelopes taking into account different solar ordinances. We are going to use the same urban environment in different locations. The first location is in Boulder, Colorado. The second one is Warsaw, Poland, and the third one is Tallinn, Estonia. The case study number 1, the analysis period is only 4 hours of the winter solstice, and the daily requirement is all sun hours. The case study number 2 is located in Warsaw, Poland. The analysis period in this case are 2 periods actually. The daily requirement here is 3 sun hours within these 10 hours for each day. The case study number 3 is located in Tallinn, and the analysis period here is from April 22nd to August 22nd. The thing is that the daily requirement here is based on the ratio of the available sun hours. So these components, the basic components, were presented in the previous video tutorial. But anyway, for example, we can begin with Colorado case study. We need to generate the analysis period component. We need to generate all the solar vectors. So we need to introduce these inputs and also to define the start month, which is the last month, and the end month. So in this case, these are coincident. The start day is and the end day is the 21st, and the start hour is 10 p.m. 10 a.m. The end hour is 14. Okay, the time step, since we have only 4 hours, we can use a lot of sun vectors, because this probably won't be time consuming as other solar ordinances. So we can select even 30 time step. That means that we are going to generate one sun position each 2 minutes. So this is really fine. Now the sun vectors, once we have generated the sun vectors, we need to generate the selected sun vectors for each window. So we need to introduce basic information. Let's define 10 degrees for the dead angle and also for the minimum altitude for all the case studies. The control geometry, we are going to keep it this like simple parameters, 0, which is means that the reference geometry is the center of the plot, and the vector cell in this case, since we want to maintain the requirement is all sun hours, we need to set this to 0. This value we are going to change this value in this tutorial in order to show what happens when we are designing in different places of the world. This vectors type, there is no point to introduce anything because we have already selected all sun rays. The context, as in the previous tutorial, we need to convert this to mesh, and we need to input the windows, of course, this is really important, and also the plot. The design core in this case, since we are using this control geometry 0, this is not necessary. Let's keep the 100 meters as maximum height, and we need to run this tool again. Okay, so as remember from the previous tutorial that we can display the selected sun rays, so we can see it from the top, and this is the basic information. We will see what happens with the computational time when using different when considering this different solar axis regulation. In this case, there is something missing, of course. Yeah, probably because we didn't run the previous one. So yeah, this is daily stuff that will happen with this. These are all the visible sun rays for all these windows for this period. Okay, so we can generate actually the solar envelope with this information already. So we will notice that obviously in this case, since we are selecting all the sun rays for this analysis period, the selected sun rays are the same as the visible sun rays, of course. But when we are using the for the case study number 2 and for the our case study number 3, these two set of sun rays will be different because we are prioritizing different sun rays among others. So we are going to introduce the selected sun vectors here and also the basic information, let's say plot. In this case we are going to select also the grid size as 9 meters as the previous tutorial, and also 100 meters also windows. The maximum height in these two tools should be the same. Actually, we need to run this tool also. We want to visualize the mesh and also the phase boundaries, like almost 18 seconds only. Well, you can see here how is the solar envelope. Actually, we can even we have here the mesh, but we can bake it actually to layer and associate it with the layer 1. But since we don't have now, we can actually record this information so we can compare different case studies. Okay, so now is the time for the case study number 2. We need to introduce the weather file and also the 2 analysis periods. So in this case, since we have 2 analysis periods, we have to define from March to September, and in this case it's the 21st in both months. And the same range, so from 7 a.m. to 5 p.m. Okay, this is the start month and the end month. This is the start and the end day, and this is the start hour, and this is the end hour. We generate the we can use 30 times the, because it will be one sun position per 2 minutes. So we generate these 600 daytime sun positions, and the main difference between this case and the previous one for Colorado is the selection of vector cell related to this type of solar axis ordinance. So now, since we have different solar ordinance, we have to select a vector cell equal to 1. As well, the vectors type, we can just leave it as 0. The vector sum is the minimum, in this case, the minimum number of sun hours. Since we have 2 periods, we need to define a list of vector sum values. We can generate this already. In 4 seconds, the tool could calculate these cells and rays, and these are the visible ones. So we can use these cells and rays, or this associated to these cells and vectors, to generate the solar envelope. This case is supposed to be more time consuming than the previous one because of the number of cells and vectors. Note that the grid size and the plot and the max height and the number of windows is the same as the previous example. So we can see how is affecting this variable to the computational time. So we have in 45 seconds the solar envelope associated to Warsaw, Poland. Okay, so we can actually bake this to layer 2 and to make the total comparison with all the different cases. And this is the third case study, Tallinn, Estonia. In this case, we need to introduce the start month is April. The start day and the end day is the same one, but the end month is August. We are going to start from 0 until the end of the day, and we're going to use one sample. We are going to generate one sun position each half an hour. Time step 2. We generate, in this case you can see the difference, 6,000 sun positions, but the die time, the sun positions associated with the die time are 4,000 in this period. And the control geometry in the vector cell option now is the number 2, because the selection, this option is for ordinances based on the percentage of sunlight hours. And in this case, we need to define the ratio of available sun hours that we need. So this value, of course, goes from 0 to 1. So we can actually generate all these sun vectors. This is going to take more time, of course, because the number of sun positions are much larger than the previous one. You can see after almost 16 seconds the selected sun rays, but we can see how it's almost not visible, the surrounding buildings. All these are the visible sun rays. These are the selected ones. So we are selecting sun rays with sun vectors with the highest solar altitude and not hitting the theoretical volume. We can create the solar envelope right now. In this case, this is going to be like more time consuming. So we have generated the solar envelope already. It's like pretty much time consuming, right? We can see only the solar envelope here, And we can now at this point make the comparison between the different case studies. So even having the same urban environment, we have different solar envelopes, as you can see here. So thank you for watching this second tutorial, and see you in the next one.